Welcome to the second half of section 5.4. We're going to work some more with indirect proofs. And all I'm going to do in this video is show you example after example after example, walk you through indirect proofs one at a time so you get a good idea of how they flow and how they work so that you'll get an idea when should I use an indirect proof and how would I use an indirect proof. And there's nothing like seeing it done or doing it yourself to learn how to do it. So let's get started with section 5.4b on indirect proofs. So here's our first statement that we want to prove. If x and y are integers such that the product of x times y is even, then x or y is even. And we need to prove this. So to prove that either x or y is even, step by step, would be difficult. This would be a great example of using an indirect proof. So remember, our first step is to negate what we are trying to prove or our conclusion. It's the same step in a contrapositive. So what we are trying to say is that either x or y is even. We're trying to negate that. So some people will think, well, then the opposite of that is either x or y is odd. That would not be correct because it doesn't negate that x or y is even. I can have one even and one odd. It doesn't negate each other. So in order to negate either x or y is even, then neither one can be even. Neither x nor y is even. Therefore, both x and y would have to be odd. Okay, so I've written down what I just said. Assume that neither x nor y is even, so that means x and y are both odd. Now, it is not uncommon in indirect proofs to deal with even and odd numbers. So how do we represent even and odd numbers? That's really important. Remember, even numbers can be divided by 2. So we can represent an even number with 2 times a variable. So an even number could be 2n or 2x or 2m or 2l, 2 whatever letter. 2 times something automatically would make it even. So we could designate an odd number by going 2n plus 1. That would always represent an odd number because we'd have that extra 1 there added to any even number. So we're going to use that to show what x and y would both look like. Okay, so I wrote that down. I designated x as 2n plus 1 and y as 2m plus 1. Making sure both of them would represent an odd number, no matter what, as long as n and m are integers. So that's the assumption, which if we're really detailed, we'd write down. Okay, so I'm trying to show here's x and y, and I'm trying to show that x times y would be even. So I need to multiply these two expressions, 2n plus 1 times 2m plus 1, and see what I get. So I'm going to write that down. So that means x times y would be 2n plus 1 times 2m plus 1. I'm going to FOIL that. And I get this. If I want to, I can simplify these 3 and factor out the 2's and all of them. But I don't really have to. The fact that this has a 4 in front of it makes it even. This is even. This is even. But what do we have at the end? We have a plus 1. So no matter what m and n are, that plus 1 is going to make this number odd. But that leads to our contradiction, and that's the whole point with indirect proofs. Because here, x and y to x times y must be even. So we write, but x times y is even. So we write, but x times y is even. That's our given. Therefore, remember that's our symbol, shorthand symbol for therefore, x or y must be even. That's the law of contradiction. That is what indirect proofs do. They allow us to use the law of contradiction to prove our proof statement. So that's our first example, and that also shows you how to deal with even numbers and odd numbers in a proof. Here's our second one. This is a geometric proof. So I have a diagram up here, and this is written out just like a traditional proof would be with our given and our proof statements. So what we are given is we have a scalene triangle, ABC. What we are asked to prove is that BD is not a perpendicular bisector of AC. To prove something is not something is kind of challenging. So this would be a great opportunity to use an indirect proof. So remember, with an indirect proof, the step number one is to look at our proof statement, our conclusion, and assume its negation. So if we're trying to prove that BD is not a perpendicular bisector of AC, then we should assume that BD is a perpendicular bisector of AC and see what happens. So that's our step one. We write down our assumption. Step two, what are the ramifications of that? So I'll talk through it and then I'll write it down. If BD is the perpendicular bisector of AC, then that makes D a midpoint. And that means AD and CD are congruent. It also means ADB and CDB are both right angles, and BD is congruent to itself by reflexive property. I have two congruent triangles by side angle side, or by leg leg with a right triangle. Either way, leg leg or side angle side. Either way, these two triangles would be congruent, which would make AB and CB congruent. But wait, what's the given? This triangle is scalene. Do you see how that is impossible? The scale, and so that, therefore, because the given that it's scalene, it can't be a perpendicular bisector. So I've proved it using the law of contradiction. I'm going to write all that out, not in a whole lot of detail and using shorthand, but that's the path we're going to go through. I'll show you what it looks like on paper. Okay, I've basically written a proof about angle bisectors and isosceles triangles in paragraph form. It's what I said. I've just written it out. Assume BD is the perpendicular bisector of AC. That means D is a midpoint and AD is congruent to CD. And angle ADB and CDB are right angles, and BD is congruent to BD by reflexive property. So triangle ADB and CDB are congruent by LL. That means AB is congruent to CB by CPCTC. Corresponding parts of congruent triangles are congruent, and that means triangle ABC is, by definition, isosceles. But here's our big contradiction. Triangle ABC is scalene. So now I write the given and the law of contradiction and how that indirectly proves BD is not a perpendicular bisector. Because if it was, that triangle could not be scalene. So here's our contradiction at the end. Triangle ABC is scalene because that was given. Therefore, BD is not a perpendicular of AC by the law of contradiction. That's how you use an indirect proof to prove something is not something. Okay, how do we negate inequalities? Because remember, we start by assuming, temporarily assuming, that what we're trying to prove is the opposite, or we're going to negate what we're trying to prove, and that is that x is less than -4. So what we're going to start with is assume that x is not less than -4, which would look like this. X is not less than -4. Well, if it's not less than -4, then by the law of trichotomy, all these different laws, what could x be? If it's not less than -4, it could be equal to -4, or it could be greater than -4. So not less than -4 is the same as greater than or equal to -4. That's how we negate inequalities. And so that's our first assumption. Okay, so we are going to assume the opposite, that x is greater than or equal to -4, and plug that in to this equation. -3x plus 4 is greater than 16. Here's our given. -3x plus 4 is greater than 16, which means -3x is greater than 12, using the addition property. If x is greater than or equal to 4, what would that mean? That would mean that, well, let's pick a number. What if x is -3? Well, then -3 times -3 is not greater than 12. It's 9. It's less than or equal to 12. So if x is greater than or equal to 12, then that would mean that -3x plus 4 would be less than or equal to 16. That's what that would mean. But that contradicts our given. But -3x plus 4 is greater than 16. That's our given. Therefore, x is less than -4. So you prove that it can't be what they say. It can't be anything else, and that's how you prove what it is. Whew, this one was a tricky one. If a plus b is greater than or equal to 20, then a is greater than or equal to 10, or b is greater than or equal to 10. One of them has to be greater than or equal to 10 in order for us to have a sum greater than or equal to 20. So we want to prove this is the case. One of them has to be greater than or equal to 10. So we're going to do this indirectly. So what are we going to temporarily assume? We are going to assume that neither one is greater than 10. What's the opposite of greater than or equal to? Less than. So since this is an or, both of them would have to be less than 10. That's what we will assume. Okay, so here's our assumption. We're negating this conclusion. A is less than 10 and B is less than 10. Notice we negated both the greater than or equal to and the ors, kind of, didn't we? Okay, so what's the ramification of that? If that's the truth, then A plus B would be less than 20, wouldn't it? Then A plus B would be less than 20, but A plus B is greater than or equal to 20. That is our given. Here is our big contradiction. So, therefore, what can we know? Therefore, A is greater than or equal to 10, or B is greater than or equal to 10 by the law of contradiction. Hopefully this has helped just to see how you do an indirect proof. Remember, what is the proof statement or the conclusion of a conditional? Negate that. That's what you're going to temporarily assume that what you're trying to prove is not true. Show what the ramifications of that would be step by step. Work through that until you come to a big contradiction, which concludes that therefore the proof must be true by the law of contradiction. Those are the steps. So assume the opposite of what you're trying to prove, step through what the results of that would be, and then draw your conclusion at the end. Hopefully indirect proofs make a lot more sense now, and if you're asked to do it, it would not be a problem at all. So that's that section. I'll see you guys next time.